So one of the things we could do with renewables, which comes closer to those concerned with built environment issues, is to move to embedded energy systems. Instead of building a power station, we can deploy a wind farm. Instead of a wind farm, a marine turbine farm. Instead of that, we could put CHP plant in all institutions. Instead of that, we could deploy renewable energy at the urban scale in houses and so on. And you can see how we could balance. Of course, these expressions are all in terms of capacity. And to get capacity to energy, we would have to have about 3 times as many deployments because they don't work all the time. So we would have 3 to 5 times as many CHP plant, sorry, not CHP, 3 to 5 times as many wind turbines if you wanted to match energy from a power station. However, it's a very interesting concept that all these micro-generators, generators of heat and power, could somehow be deployed in the built environment. And here's the model. We take the built environment. Those who understand these things can enact demand reduction and reshaping technologies in order that they can size and deploy combinations of these micro-generators in such a way that they can match better the demand. And then the built environment goes to the public supply connection, electricity, gas, and whatever, to make up the residual. So it's a cooperative model. If these are network disconnected, the network will then see a diminishing load in future because these micro-generators operating in harmony are delivering heat and power into the built environment and reducing the demand on the national infrastructure. Alternatively, there'll be those who will argue that these should be schedulable. So the utilities would want to be able to turn them on and off in a planned way. And that would be the sorts of things you're seeing now with feed-in tariffs, where you can generate using renewables and you can sell the excess into the grid and you can get a financial reward for that, and you can also claim because you've generated something that displaces the need to take from the grid. So there's all these different mixes. The more you move towards network connected, the more you're going to need active network control, and that doesn't exist at the present time. And we've got some way to go to elaborate that. The more you do it disconnected, the more it's to do with fundamental design that architects and M&E profession have to get involved in to make sure that the balance is right. And of course, the whole thing in future is the built environment is going to become very, very closely related to hybrid and electric cars because they're a storage device for energy. And you'll be able to utilize that in the picture somewhere. So that's the embedded generation concept, which drives us down with renewable deployment. And there's an example in the city of Glasgow of the Lighthouse building, where it demonstrated this notion of grid cooperative embedded generation, whereby transparent insulation, advanced glazing, and smart control systems were used to re-engineer the shape of the demand profiles for heat and power. And then PV, ducted wind turbines, and PV integrated with ducted wind turbines, PV was the spoiler on the ducted wind turbine, were deployed, and a hybrid PV facade giving heat and power. And what basically came out of the study, and it's an actual deployed demonstration project, was that the renewable potential was greater when integrated than the demand, but because of the temporal mismatch, we still had to go back to the public electricity supply. So there was substantial energy reductions, but you can't do it all by renewables. And if this was to become an exemplar model for the future that the profession wanted to adopt, then these would be the sorts of challenges that the profession would have to take on and understand, working with the grade. That's an exergy analysis, so the usability of the energy. Learning how to design hybrid systems and not just a standard conventional HVAC system. Developing strategies for the cooperative control, and then all the active network management if it's grid connected. So there's big challenges there. So the challenges for those who work in the built environment, I won't read out this list, But we can't say that the challenge now is to reduce carbon emissions. And that's it, carbon emissions. And therefore, everything you do has to have a carbon index or a carbon footprint calculation, because that just defies logic. It's not. It's to ensure requisite levels of thermal, visual, and acoustic comfort for human beings, as it's always been. That's first. To make sure that we've got good indoor air quality, so that we can promote health and productivity goals. To make sure that we alleviate fuel poverty. We're not giving expensive systems that require less spent on running costs and more spent on maintenance, for example. We need to make sure that we've got innovative approaches to energy efficiency. We need to make sure that all the environmental emissions and impacts are mitigated or held in check. We need to make sure that demand and supply is being matched. We need to make sure that our local new renewable systems are well deployed. We need to make sure that everything's being managed well and intelligently. We need to make sure that there's actions at the community scale, because some deployments need more than one entity. A district heating, renewable heating scheme, a CHP scheme needs a community action. We need to make sure we conform with all the growing legislative requirements, and so on. How are we going to do that? There are no paradigms. There are no rules of thumb. What we need is explicit computational tools which emulate future reality at the design stage. And that was, it seems to me, the destiny of computer technology in our profession, was to enable that virtual design, enable you to prototype and test the design artifact in a wholly rigorous way, with no assumptions or limiting assumptions made, so that we can make sure before we deploy it's robust. And that needs next generation integrated dynamic prediction tools. And they need to be fully integrated in the design process. And that's what this diagram says. It says we're not talking here about a computer program that's on your PC, and at some stage in the design process you go off and you type in some data and you get some graphic out, and that's it. We're talking about design integrated comprehensive tools, so that they're there within the design environment. You don't have to be a guru in advanced, detailed, integrated dynamic simulation. They're just within your design environment. And as you describe an artifact, so you get the reward of the performance prediction. And that's how I'd like to finish the presentation, by describing what these tools are, what they do, and how they can be integrated within the design process.